Hello and welcome back to Civil Field Trainers. My name is Shadab. Today we'll be designing a one-way slab by using this given Excel sheet. Alright, so off the bat you can see this is our Ly and this is our Lx. Okay, please remember, just for the sake of ease of calculation, always the short end is going to be Lx and the longest is going to be Ly. So if you see here, panel size I have given 8.3 and Lx I have given it as 2.30. If you want to change this, you can change it to, say, for example, 5 and 2.3. But if you decrease it, for example, if you make it 2 or something, you can see it will change it to 2 over here. I have given that condition over here. Okay, so let me make it as 2.8.5, whatever it was, and this is 2.30. All right, so this is our simple one-way slab. Now this panel can be taken from your AutoCAD plan or it can be taken from your ETABS diagram, whatever it is. You take that values from there. Then your whatever FCK value you have taken. For example, if I'm taking M20 as my grade of concrete, I'll take F20. Take 20 over here. You can open up the drop down. You can select accordingly. Generally, M20 is more than sufficient for your slabs and beams. Then we have F of 5 as 500. If you want to increase it to 550, you can do it over here. No problem. Then we have our clear cover. Clear cover is what? Basically, clear cover is our 20. We generally place the blocks underneath the rebars, right? So that is our 20. So whatever is there in yellow, you have to fill it from your own end. All right. So this is basically our one-way slab, and this is what you have to take input in the very first step. Then we come to the second step. It will do Ly by Lx. Basically one way, two way. It will try to find out if it is greater than 2, it is one way. If it is less than 2, it is our two way. Then we have assumed D. For example, if I take it as 150 mm as my slab depth, see, generally for a slab as big as this, we go anywhere between 5 to 6 inches of slab, right? So I'm taking 6 inches of slab, basically 150 mm, and if later on we can revise the size to 125 mm, no problem whatsoever. Okay, then this is our depth. Then the dead of the slab is basically, I've given the formula over here. Double click on the formula, double click on this, and you can see here. So D into 25, that is basically a density of concrete divided by 1000. You do that, you'll get kilonewton per meter square. You will get your dead load of your slab. Okay, everything is calculated per meter square. Then floor finish, you basically know IS 875 part 1, IS 875 part 2. You can go and refer those code books and you can find out your floor finish and like whatever your live load is. You can take the loads from there. Once you have done all of this, you have to combine all those loads. So I've taken a sum over here and you get 8.25 as your total load. Okay. After doing this, next is DX provided. So I'll just take you to the paint and explain to you what we are doing over here. So if I just open this, so for example, if this is my slab, okay, this is my slab, and what is my slab depth? My slab depth is currently 150 mm. Okay, let me just take this from here. Okay, let it be here, no problem. 150 mm is my slab depth. Now, what is basically happening is I'm telling you that this entire depth is not going to come into the calculation part because we have one beam, sorry, we have one rebar, okay, that is going to go from here to there. All right, and there is some space underneath this rebar that's called as clear cover. All right, so this clear cover of mine is basically somewhere around 20 mm. Okay, this clear cover of mine is something around like 20 mm. Then this rebar is there, right? I'm taking d by 2. So if I'm taking, assuming my dia to be 10 because the slab is 8.5 by 2.3, I'm assuming it to be 10. Okay, whatever is in yellow, you have to input that value. So if I'm assuming it to be 10, what I'm going to do, I'm going to do 10 divided by 2. Okay, so something like 5 I'll get over here. If I can just take it a little bit top, something like 5 mm. Okay, so what I'm doing is whatever is the left, this distance of my slab. Okay, what is this distance of my slab? It is basically 150 minus the clear cover minus d by 2 if I have to. I'll get something like 125 mm as my effective depth. Okay, 150 is total depth, 125 is effective depth. So I'll get 125 mm from where? From basically this point to my this point. All right. So if I come back to the Excel sheet, you can see 1.50 into we have done this entire calculations over here, and then 125 is there. So you can see I've given the minus signature over here, no? So if I double click on this, you can see I have taken 20. This is my total depth minus 20 minus d by 2. Whatever my dia of bar is there, that is 10 mm divided by 2. If I do, I'm going to get 125 mm as my DXR effective depth that I'm taking. Then we have to take effective span. Now effective span, I'll take you to the code book first and we'll discuss the code. I have to take you to page number 34. So if I take you to page number 34, if I just go up 34, you can just read the condition over here, right? We have two conditions basically. The effective span, that is basically the L, can be two things. One, it can be clear span plus the effective depth. Okay, so it can be clear span plus depth of slab or beam or center to center sub supports. Okay, so basically what they are trying to tell you is if I take you to the paint again, either you take span, or whatever span is there, you take span plus the effective depth that we have calculated. Okay, you take this into your consideration, or what you do, you take span plus, if you see, beam width. Okay, if you just read it over here, center to center of supports. Okay, so what we have for slab, we have support as beam, no? So span plus our beam width, it will be there. Okay, so basically if I have a beam over here, okay, and if I have a beam over here, I have to take center of center distance. So let me just change it to green. So from this center to that center, I'll run from here to here. Okay, so basically it becomes d by 2 by plus whatever that width is, w by 2, w by 2. If I do, I'll get the entire width. So basically I have to take what? I have to take the lesser of these two into my consideration. Generally span plus effective depth is going to be less. Okay, so if I just mention it over here, for example, if my span is like 2 meters, for example, let me just expand this. Okay, so if I do span as my 2.3 whatever is there, plus if I do my effective depth is currently 125 something, 2.3 plus 125, again this is an mm, so it will be 0.125. I'll get something around the range of 2.3 plus 0.125. I'll get 2.42 something, 2.42. Okay, in my second condition I'll get 2.3 plus half the distance of my beam width. For example, if I have a 230 beam width, so it will be 0.125 plus 0.125. It will give me something like it will be 2.3. It will be 2.3 plus 0.23, it will be 2.53 meters. Okay, so generally what happens, your span plus effective depth criteria is the criteria that generally takes over the lead. Okay, so because the condition whichever is less. Okay, so which is less over here? 2.42 is less, no? So span plus effective depth is less, right? So that is why directly I have given that condition to you over here. Okay, if you come for this one, it will be short span plus dx provided. Okay, effective depth whatever is there, that I am considering directly. Okay, I'm not giving you two choices over here. Directly I'm giving you one choice, which is this. If you want to consider, you can consider, no problem. Okay, you can put the or condition over here and you can satisfy it. But generally speaking, the slab depth is 5 to 6 inches, so always this will give you the lesser value, and the beam minimum will have at least 230 width. Okay, so 99% of the times the the criteria of this one, that is span plus depth, is the one that wins. Okay, so I'll just come out of here. So this is the code book, the clause which I have used. You can see I have mentioned along with the page number I have mentioned. You can come and check it again, no problem. Okay, so in the code book they have given us two conditions. I'm directly giving you one condition here. I'm telling you why I have done that. I have explained in the paint here. All right. So once that is done, now factored moment, basic WL square by 8. Okay, 1.5 IML time because I'm doing the factored thing. Let me just zoom in a bit more. Okay. Yes, okay. So factored moment, I'm doing 1.5 because it is factored into WL square by 8, 9.10 kilonewton meter I'll get. Then factored shear, WL by 2 into 1.5 because I'm doing factored, I'll get 15 kilonewton. Then we have effective depth required. This formula is there here. See, mu is equal mu by 0.133 FCKV. Everything is in square root. And this I'm taking from IS 456 annexure A. I even mentioned the section. And you can see here, when it comes to the formula, no, this formula, I have taken 0.133. Okay, I have taken what? I have taken 0.133. Why I have taken 0.133? Because I am doing FE 500. If I do FE 550, it will be different. If I do FE 415, it will be different. Okay, so you have to, based on whatever you are using, you are supposed to change this formula a little bit. Okay, instead of 0.13 to 0.138, see, there will be no drastic difference. Okay, because we're in decimals. But if you want to be accurate, you can do this, no problem. Okay, so I have given a note over here, change formula based on the FE steel used. So if I'm using FE 500, I'll stick to 0.133. So I have to just double click over here. You can see the formula is not this one, this one. Wait. Yeah, this one, 0.133. So once this is done, then I have to do total depth. See, whatever I have minus here, no, to get 25. Now I'll add it. Okay, what will I do? I'll take 58.48 plus my effective span. Sorry, my clear cover 20, and then my d by 2, whatever I have removed, I'll just add it up here. So if I just double click on this, you can see the formula again. Okay, so this is basically what I have got from the formula, plus what I am doing. I am doing the clear cover plus I am doing d by 2. Okay, so if I do that, so my effective depth is 125. Okay, and my total depth is 150. So I have assumed 150, but if I take 183.48, it should satisfy it. Okay, what is my what is my total depth? 150 mm is my total depth. But as per the code book, as per the clauses, if I take 83.4 also, my slab is safe, no problem whatsoever. But the thing is, this is not practically possible. If I take you back to the paint for a second, generally what happens is whenever you have slab like this, no, we have electrical conduits that sit here, fan, okay, be it light, whatever is there, the conduits will come and sit, and whatever bars you're running, no, the electrical conduits, they'll run something like this, okay. So you need to have at least a minimum of 4 inches thickness for your slab, okay. Generally 5 is best, so anywhere between 4 inches to 6 inches you need to have. In my experience, 5 inches to 6 inches is best. Okay, 4 inches also will work for you, no problem. But this electrical conduits will create some kind of problem. Okay, because you have to give the clear cover also and everything, and you have to maintain all of it. Okay, while you have all these conduits coming and setting along with this clear cover and everything, along with this rebars and everything. So 5 inches to 6 inches is best in my experience. Okay, so coming back to your Excel sheet now. So what we have done, we have found out that whatever assumption we have made, the assumption was 150 mm, but as per the code, 83.48 also is fine. But I have explained to you, 5 to 6 inches is the minimum, like optimum depth of slab you can give. Anything more than this will be too much. Okay, 4 inches also will work in certain criteria. No, it's not like 4 inches will not work. So total depth is there. After that, AST is equal to 0.5 FCK FOI BD is there. The entire formula is mentioned over here. And for reference, I'm attaching a YouTube video for you. Okay, instead of creating another video for derivation, one already exists. So I've attached this the derivation video for this formula. And again, I'm taking 1000 mm as my width. So I'm not doing the entire 8.50 meter. I'm just doing 1000 meter per. Okay, 111. I'm just doing it. All right, and because see, I'm not going in 8.50, I'm going in 2.30 because all my calculations are for what? 2.30 only. Okay, effective span. So instead of doing the entire 2.30, I'm just doing 1 meter now. Then I'll do 1 meter. It's like that. Okay, the design will not change, but we are just for the sake of ease of calculation, we are just doing it as per meter. Okay, so now we have to use the formula 0.5 FCK for 5 BD, whatever this is there. You input all these things. If I just double click, you can see I have input the entire thing, and you can see the value is 174 mm square. All right. Then we have AST minimum 0.12 BD. This is AST minimum. We get 150. So what happens now is you have to cross verify which is higher. Okay, if AST minimum is higher, you go for AST minimum. Okay, as per the code, at least this much amount of steel should be there in your slab. But if the AST is higher than the AST minimum, you have to go for that. So AST required, you can see I've given a condition of max. Max of these two, it will select automatically. You don't have to do anything. Okay. So once that is done, we come further down and you can see main bar and secondary rebar. Again, whatever yellow is there, you have to fill in yourself. So I have taken 10 and 8 as my main and secondary rebar. All right. Then after this, I have to come for the spacing part. So spacing part will be somewhere over here. In the spacing, I have to take it to page number 46. So I'll just take it to page number 46. I'll just go here, page number 39, 30, 40, 44, 45, and page number 46. Okay. So page number 46, you can see here I've got two conditions: horizontal distance between parallel rebars. So instead of reading the entire thing, I'll just show it to you. 3 times the effective depth of solid slab, or 3 mm, whichever is smaller. Whichever is smaller, again, this is very important. Whichever is smaller. So basically what is happening here is I have to assume that I have bar. So whatever assumption I make here, for example, instead of 10, okay, just keep an eye out 10 over here. If I make it as 12 over here, automatically it will change to 12 over here. If I make it like 7, automatically it changes to 7 over there. We don't have a 7 rebar. That's a different story. So just go for 10, 12, 16 or 18. So 16 or 20. We don't have 18 bar also. But in slabs, generally 10 to 12. 12 also is too much. 8 and 10 is what we generally give the rebars in. 12 rarely I have seen in criteria, where we have huge spans and all. There we have provided once or twice, but generally 10 is sufficient in your slab. Don't have to go for 12 also. So 10 dia bar is what I'm providing here. So automatically whatever I change I make here, automatically it will get updated over here. Okay. Then spacing required, AST by AST required I have done. Spacing of 1 bar by the overall spacing. If you do that, you get the amount of spacing required as 451 mm. And if you see here, there's an upper cap. Upper cap is what? 300 mm. Okay. So whatever is beyond 300 mm is waste. We cannot provide that. The code is actually telling you 3 times of the effective depth of solid slab, or 300 mm, whichever is smaller. Right? So what is smaller here? You have to check that. So 3D I have taken from the clause, 300 mm I have taken from the clause, and spacing required I have taken from here. AST by AST required, 450 mm if you provide, it will suffice, they are saying. That, but why am I getting 200 over here? That is because I've given a criteria there. If I double click, you can see minimum of these three, comma 200. Now why have I given 200? That is based on my own experience. Now if I come for the normal slabs, generally basically what happens is, if I have my slab going in this direction, let me just change the color to black, and I have my rebars running in this direction, main rebars, because I'm doing one-way slab. Okay, so what I'm basically telling you right now is, if you provide 200 mm center to center spacing, okay, this is the optimum value for me. This is what I'm trying to tell you. The 200 mm center to center spacing. Okay, 200 mm center to center spacing is what I'm telling you. Generally, some people, what they'll do, they'll provide the spacing as just change it to this. Okay, they'll provide the spacing as what? They'll provide the spacing as 250 mm center to center also. Okay, people do this also, but in my experience, 250 you can do it if you're standing on the site and you have control over it. If you don't have control, you're sitting somewhere in your office and someone else is doing execution on the site, please make sure that you check the spacing properly. After a point, when you go to the site, when you look at the rebars, you'll get an idea what kind of spacing they have provided. That much experience you will gain eventually. Okay, just by looking at the bars, you can tell how much of spacing they have given. All right. So if you give 200, what they will do on site? They'll provide 225. Why? Because so that they can save the money on rebars. That's what they'll do. Okay. But if you are standing on the site and you have control over it, then go for 250 mm, no problem whatsoever. Okay. But to be on safer side, 200 mm is what I recommend. This is what I design. All right. So if you want to change it to 200 to 250, you can just change it over here, and the values will vary accordingly. All right. But if you're not on site, you don't have any control over the execution of the project, make it 200, because tomorrow if something happens to the project, okay, you can tell them that I have given them 200, they have provided 250 mm. Frankly speaking, you should be on the site when the steel work is going on, and you should sign on the site and everything you have to do. But majority of them don't do all that paperwork. Okay. So let me just minimize this and come back to the Excel sheet. So whatever you want, you can do over here. Generally, I keep it as 200 mm. If you want to make it 250, it is up to you. But don't go and provide 150 and all. Okay, for small projects like this. All right, if you provide 150 value and all, then you have number of bars will become more. Okay, so for example, if you provide 150, it will be 150 something. It will look something like this. Okay, so then what happens? Your project will become uneconomical. Too many. You'll have this rebars. If it is required, only then provide it. Don't try to play it over safe. Okay, by giving 150 and all, don't do that, because if you see here, for 200 also, it is giving you a good amount of value of AST. All right. So for example, what is basically happening here is, if I have to explain it to you, see, let me just minimize this a little bit. Okay. See what is happening. My requirement is 174 mm. You can see here my requirement is 174 mm. But how much am I providing? I am providing 392 mm. All right, almost double I am providing than what is required. All because I am giving 200. If I make it 250, you can see from 392, it will decrease to how much? It will decrease to 314. Okay, and as I have said, if you're on site, if you're standing on site, if you're controlling the entire the execution part, only then go for these values. Otherwise, don't go. Because when you give 250 also, they'll provide 300 on the site. They will do anything they can to save money. Okay, so I'll just give 200 for now. All right. So what is happening, basically I'm giving 10 mm at 200 mm center to center. Okay, so basically 10 dia bar at 200 mm center to center is what I'm providing for my main bars. If you go for your spacing rebars, for spacing was basically what is happening, again 0.12 BD is there and 5D and 450 mm is there. If I just open it, there's a basic second condition that is shown over here, that it is 5 times the effective depth, the first, or 450 mm, whichever is smaller. Again the same thing over here. Again for this one you can give 250, no problem. If you see the condition, minimum I have given us 250 over here. Okay, some people even give it 300 also, no problem whatsoever for the distribution bars. Okay, again this from this I get is 0.12. Again, if I just take you to the code book, page number 48, we have that clause. Page number 48, here we have that clause. Okay, so if you see here, minimum is the criteria we have taken here. No, this one 0.12 BD as 150 mm. From where did we get that? We got this from page number 48, clause number 26.5.2.1. So if you see over here, the mild steel reinforcement. Okay, if you're using mild steel, you'll go for 0.15%. But we don't use mild steel. What do we use? We used HYSD bars. So high strength deformed bars is what we use on site. So we are going for 0.12%. This is what the code is telling us basically. A minimum of 0.12% of your area BD should be what? It should be of rebars. Okay. So 0.12 into B into D is what is the code is telling you from this particular clause. So again, 5D is there, 450 is there. Spacing required is we are getting something like this. So lesser of the above three, I have taken as 250 mm over here, and based on that we get some amount of reinforcement that we provided. So whatever I have shown here, no, it is coming over here also. So provide 150 mm thick slab having 10 dia reinforcement, 200 mm center to center for main reinforcement, 8 mm dia at 250 mm center to center for secondary reinforcement. Okay, so AST required is 174, AST provided is 392.5. Alright, again I'm playing safe over here. Next we have shear calculations. Tau is equal to VU by BD. From where do we get VU? VU is nothing but your factored shear 15. So VU by BD you do over here. Again B we are taking as 1000. Everything we are doing per meter. Okay, for the sake of ease of calculation. Then tau we get as 0.12. 0.12 Newton per mm square is what we get as tau V. Then I have given refer the adjacent calculations for your tau C value. So you have to come over here. You have to open up page number 73. So we are at page number 53 something. Let's go for page number 73. 67. Okay. So you have to come to what? Page number 73, page number 78, table number 19. Okay. So you have to do 100 AST by BD, and here when you do 100 AST by BD, you cannot do AST required. Okay, you cannot take 174 into calculations. You have to take what? You have to take the AST provided, that is nothing but 392.5 into calculations. When you take this into calculations, your PT value will be 0.314. Okay, it will be what? 0.314 is what you are getting. So basically you come over here. So 0.314 comes between 0.25 and 0.50. You get 0.314. M20 is what I'm using. So 0.36 and 0.48. In the middle of these two values, you'll get your tau V value. Okay. Again, I have given that you have to calculate the thing by using interpolation. I have not used the interpolation formula over here. Just use a calculator and you can do it very easily. Okay. It's hardly two or three steps. So you do the interpolation there and you get tau C value. That's why I have given this in orange, not yellow, because I have to perform some calculations, minimum calculations. Then you get your tau C value. But tau C is not the ultimate value you're supposed to consider. You are supposed to go up. Page number 72. If you go for page number 72, you will come across this clause. Okay, 40.2, design shear strength of concrete. For solid slabs, the design shear strength of concrete shall be tau C into K. What is K? K is nothing but a factor that is depending upon the depth of the slab. So if I'm using 150 mm or less, 150 mm or less of my slab, the K factor is going to be 1.30. That is what I have considered over here as 1.3. Want to put 1.30, you can put 1.30, no problem. Okay, so K into tau C, it will multiply 0.52 you will get. See, whatever this value is there, this is the design shear strength value. Okay, this is the maximum shear stress your slab can take from the code book. Okay, based on this given criteria. What are the criteria? The criteria is basically the kind of grade you are using, the kind of PT you have, and the kind of depth you have. Okay, based on these three criteria, your design shear stress maximum what it can take is how much? It can take up to 0.52. So whatever design shear stress you're getting from the calculations, it should be less than that it can bear. Okay, so tau C is something it can bear, tau V is something it is being subjected to. All right, so always tau C value should be what? Greater than tau V value. Okay, the tau C value, the design shear strength, the maximum it can bear should always be higher than what it is being subjected to, tau V value. Okay, understand it like this. All right, so if you have the capacity of lifting 100 kilos, for example, and you're being subjected to 20 kilos of weight, lifting 20 kilos, so what? You're safe, you're not going to go under failure. Okay, but if someone is putting 110 or 120 kilos of weight on you and you're not able to bear that weight, then you go under failure. Okay, I'm giving a very simple, very dumbed down version of the explanation. Okay, tau C is greater than tau V, so 0.52 is the maximum it can take. All right, so whatever value you should get should be less than this value. So I'm getting 0.12, so it is what? Basically it is safe here. Next we come for the deflection criteria. So in the shear criteria it has passed, right? Now we come for the deflection criteria. Differential criteria, I have to take you back to page number 34 again. So let me take you to page number 38, I guess, not 35, 38. Just two more a bit. We'll go to page number 38. 37, 38. Okay. So you can see here, your FS is there here. We have percent of tensile reinforcement, modification factor. Now what do we want is modification factor. Okay, percentage of reinforcement is already there with us. We have calculated this as 0.314. That is what our calculation says. Now modification factor we have to find out. So basically what I'm supposed to do, I have to calculate Fs value. Fs value is basically what? 0.58 into f of 5 into area of cross section of steel required by area of cross section of steel provided. So we know what is required. 174 was required and provided is 392.5. So based on all these criteria, basically what I have done, see here, my code book 0.314 somewhere it will come over here for me. 0.3 it is 0.4. So 0.3 something it will come over here, very minimum value, it will go somewhere on the top, and my Fs value is how much? My Fs value is approximately 129. Okay, so it is 120 here, so it is 145, 120 and 129 something it will come out somewhere over here. Okay, and 1.13 somewhere it will come over here. So the graph ends here. Okay, so what I have done, I have used the log formula. Okay, I have used the log 10 formula, and based on this formula it will calculate the MF value for you. Okay, all the necessary things are inputted into this, and it will just calculate the value for you automatically. Okay, what is the AST provided, AST required, everything will take into consideration, and it will just calculate the your modification factor, MF value it will calculate. So once the modification factor is calculated from the code, we know now for simple supported we have 20. So this you have to, this modification factor you have to multiply this 20, and you will get LYD provided as 62 something you will get. Okay, then what is supposed to do? You are supposed to take D on the top, 62 to the bottom. Basic cross multiplication is supposed to do, right? So L by 62 you will do to get the D required for what? Deflection criteria. Okay, just simple cross multiplication if you do. If I double click here, you can see that 62 is where it is in the denominator. Okay, so F22 is basically what? My effective span. My effective span into 1000, because it is in meters, I have to convert it into mm. Once I have converted into mm, then what happens basically here is divided by 62 if I do, I'll get my effective depth requires 39. So 39 is less than 125 mm. Okay, so it is safe. All right. Like this, you're supposed to carry out your entire one-way slab discussion. Actually, this the thing was requested by our students over here. So I have already uploaded the video, the file over here. Okay, I'll re-upload the file. I'll add it to the drive also. You can access the file from the drive directly. And if you want access to all these things, you can come and make a purchase here. ETABS, and RCDC. All our files are available over here, including the beam detailing Excel sheet and the column detailing Excel sheet. Okay, this is the third Excel sheet that I'm adding to the course. Again, for the Ganesha festival, we have a discount coupon running right now. If you are interested to come and join the training. Okay, again, this is a pre-recorded course. All right, so all these files are already available here in our premium group. I'll upload it to the drive also today, so you can have access by the end of the day. Okay, so if you have any doubt, please let me know. The entire explanation I have explained properly. See, the two-way slab, I won't do all this explanation. Okay, here I'm doing explanation completely. I have given all the formulas and everything. For two-way slab, directly I'll tell you what to do. All right, hopefully the next video will be on two-way slab. I'm working on the sheet right now. Okay, so please refer all these code books, whatever mentioned here. Just refer all this code book clauses and everything, and you'll be able to do the design. And if you're someone who doesn't want to make a purchase, you just want to make the Excel sheet, you can just see here. I'll double click on the formulas. You can pause the video and just input this formulas. It hardly take 2 to 3 minutes to input this formulas. Once you have inputted the formulas, you have a ready-made Excel sheet with you. Okay, it's very simple. Whatever formulas you have to put, you have to just given the formulas here in the Excel sheet format. Okay, so if you have not, let me know. Like this, you're supposed to solve the entirety of your Excel sheet. And one more thing, instead of giving 150 mm, if I make it as 125 mm for now, okay, 125 mm, enter if I do, this becomes 100 mm, and effectively you can see instead of being 0.12, it became 0.14 now, our shear. Now what I'll do, I'll decrease the steel further. I'll be like, okay, fine, I'm the one who's standing on the side. I have control. I'll make it as 250 mm center to center spacing. So what happens then? The value will further become 314. Okay, so you can see the value has increased from being 36, 37, something like that, to 61 now. Okay, so this is a much better, more economical one-way slab design. So like this, you're supposed to go and do trial error to get a very good economic design for your project. Okay, so with that, I'd like to conclude this Excel sheet. I'll provide the same Excel sheet, all the same values to all the students who are part of this course. Again, I'll upload the file today. All right, so see you guys in the next class. Thank you.